Dr. Abe Samant is Chief Software Engineer of Aerospace, Defense, and Government Business at National Instruments. Please welcome Dr. Samant.
Greetings and welcome to the presentation titled Data Streaming from SDR to Servers for Cognitive Radar and EW Applications, presented by David Asplund and Abhay Samant. My name is Abhay, and in this presentation, I will first be talking to you about some of the application requirements that we are seeing from cognitive radar and EW applications as it pertains to high channel count, heterogeneous compute systems. And then David will be speaking to us about the work that he has been doing on system topology and some commercially available servers that will enable such kind of applications. So speaking from an applications requirements perspective, if you see across the applications of cognitive radar and EW applications, you see there's an ever increasing need for higher levels of autonomy in such systems. Not a few years ago, machines would essentially use pre-acquired data, either from prior measurements or data saved in databases, and then use either supervised or unsupervised machine learning on labeled and unlabeled data sets to make certain decisions. Right? And then over time, that has moved into the area of what researchers call the knowledge-aided adaptive processing, where the information is used to draw connections across multiple objects, and that helps with applying some of these learnings and also analyzing it. To today, where there is a lot of emphasis on evaluating and creating new experiences, which is where some of the higher level cognitive principles of intelligence, language, attention, perception, and memory is coming into play. And so this is one need that is shown, and there's active research going on in all of these areas, which is reflected by the graph or in the graph that's shown on the right-hand side of the screen of the slide, where we see the increasing number of publications that are being done that are shown on Google Scholar over the last decade or so. Also, what's interesting to note is we are seeing this technology being used in multiple application areas, not just in aerospace and defense, but also in the area of transportation, for commercial 5G applications, and for cognitive radar, radio type of applications. So, so it's pretty obvious that the application space is wide. So, what are some of the challenges that people are facing today when it comes to doing cognitive research? Well, one is the convergence of data from multiple sensors and the knowledge that is being gained from this cognitive principle. So it's no longer just a two-dimensional space. It now has mapped itself as into a three-dimensional space where both of these concepts are brought together. And on the right hand side of the slide, I've used transportation just as an example of where cognitive radars are used. But this kind of picture shows you the amount of data that is coming in. Any traditional autonomous vehicle today has multiple sensors, such as cameras, radars, ultrasonic sensors, maybe lidars, that is used in object detection. But also has communication principles or communication devices on it that is allowing it to pull data from multiple cars around it. And so all of that information together with knowledge that is saved on the databases is what goes into a system level decision making process, where the agent that is running on that system is deciding between multiple set of actions. And essentially what it is doing is providing a probability distribution function of different actions that the actuators can take that is going to maximize the reward signals. So reinforcement learning, which is the newest form of machine learning that combines all these principles, is putting more and more new demands on the system that can be used for doing cognitive research. So at National Instruments, we are working actively on researching how can we put together a high channel SDR count system along with heterogeneous compute systems that combines CPUs, GPUs, and FPGAs with streaming data from the SDR to the to the SDR, from the SDR to the CPUs for doing this kind of processing. And I put together just two use cases. I'll focus on the second one. Just imagine that you have a 2 gigahertz bandwidth signal and you're sampling with a 16-bit ADC DAC, Just at sampling at 2.5 gigasamples per second, you are looking at combining about 80 gigabits per second amount of data per channel. And even if you have just two channels, the data is going to scale up to 160 gigabits per second. So that kind of shows you just the large amount of data that is being streamed from the SDRs to the processors. So with that application requirement as a framework, I'm now going to turn it over to David, who is going to talk to you about the work that he's been doing for system topology.
So my name is David Asplund. I work with Epye on our building out some of our SDR systems. And when you're building out these SDR systems, first thing you do is you start acquiring the requirements for this system. And one of the first things you want to start figuring out is how you're going to be moving data through this system. It doesn't matter what you want to process. If you can't get the data to the processors, the whole thing falls apart. So we're going to first look at some system topologies that will enable the data movement that our application requires. And then from there, we'll look at some commercially off-the-shelf equipment or commercial off-the-shelf equipment that enables those system topologies. So first, we'll imagine an SDR system with 16 SDR devices. And each one of those devices can send 1 gigabyte, actually up to 2 gigabytes per data to us. And they send that data to our server via a 10 gigabit connection. And then that server needs to take all those connections and aggregate them in some way. Well, if you need to aggregate 16, maybe even 32 10 gigabit connections, one of the first ways you would think about aggregating this data is to first put a switch in between all of these networked SDR devices in your server and have the switch connect all 32 of those 10 gigi connections and then funnel them down into say 8 40 gigi connections or 400 gigi connections. And this is it's an intuitive way to sort of aggregate the data into a single server, but it does have some challenges associated with it. One of the first challenges associated with a system like this is that the switch itself is very expensive. If for folks who aren't familiar with high-end switches, a switch like this that we're talking about, 32 10 gigi connections, 8 40 gigi connections, they start at $10,000, they go up to $20,000, $25,000. So what you're looking at is a system where the switch itself, just to get the data to the server, costs half as much as the server. It's already a strike against this switch and server topology that we would initially start looking at. And then once you dive a little further, say, okay, we've got this switch, we move the data into the server through several NICs. Now we want to move the data into our application, maybe do some light processing on that data, and then move it down onto a storage device. Well, let's break that down. Let's look at exactly what requirements a system will have in order to move data in that way. So first, in order to even get the data to memory, we need to DMA the data from the device to a memory buffer, and that's done using the OSI network stack. It would get DMA'd to the kernel buffer that the device driver owns. That device driver would live in the kernel stack. It would then transfer the data to the application, to the user space where the application lives. And in order to do that, it needs to access or hit the memory several times. First to read the data back out of the buffer, again for read for ownership, do the context switching, and then again to write that data back into the application's buffer. From the application, we then read it out, do some processing on it, put it back into our application buffer, and then finally, in order to get it onto a storage device, we would read it back out, send it to a DMA buffer owned by the storage device's device driver, and then finally send it back down. And so what this means is, in order to move a single gigabyte of data through our system to storage, we end up with a 10x multiplier on our system, on our memory bandwidth. So 10 gigabytes of memory bandwidth just to move a single gigabyte through. And what you realize is when you start to hit these higher channel counts, have these higher throughputs, is even a high performance server is unable to meet the memory bandwidth requirements when you just use the first available sort of software architecture and hardware topology and system topology. Problems immediately start to jump out at you. And actually, the more you dig, the more problems you find with a system topology like this. If we look back at arrow number 1 there, moving the data from the NIC to the DMA, this is actually based on an interrupt system or interrupt architecture, where the device driver isn't polling the device to see if data is ready. What it does is it waits for an interrupt from the device to say, hey, I've got data. Hey, I've got data. Hey, I've got data. But the thing is, in a high throughput system, there's always data available. There's always data arriving, which means you get this interrupt storm, because it's not just one network device driver that's constantly saying, hey, I've got data. You've got 16 of these network interfaces telling your operating system, hey, I've got data, come get it. And what happens is you end up dropping packets because you get this, the buffers on those devices fill up because the interrupt queue has just been flooded because you're using the standard OSI network stack to move data in a way that it was not intended to be used. The standard network stack is intended for low throughput, many connections, not low connections, high throughput. So if this isn't a good system topology for our application space, what might be a better solution? And a better solution would be a direct connect topology, where we connect each one of our devices directly to the server that we're going to be aggregating our data. So if we have, say, 16 devices, we would take a 10 gigabit link and we would connect it directly to a network card on the server. And we would use a quad port network card, something with 4 SFP plus ports on it. And each one of those ports would show up in the operating system as its own individual network interface. And so that would allow us to connect to 16 different devices and pull our data into our system. And this immediately has several advantages. The first one is this is a lot cheaper. We're not spending $10,000, $20,000 on a switch, on those high performance switches. Those network cards that you see, those quad port network cards, those cost like $400 each. So we see an enormous amount of savings or cost reduction by going to this direct connect. But more important is it also enables better performance. Earlier we talked about how the OSI network stack requires an interrupt-based architecture that immediately floods or that gives you an interrupt flood or interrupt storm that floods your interrupt queue. Well, if we instead move to a direct connect model, we don't need to use the OSI network stack. We get access to things like DPDK, which, although you can use in a server and switch model, are far easier to implement with a direct connect type of topology. And this is something that's actually already implemented in certain drivers, like UHD, for example, where what you can do is out of the box, you can assign a network interface to run only on a specific core on a specific processor. And what that will then do is it'll just sit there and it'll pull the device. It'll pull the network interface and say, give me the data, give me the data, instead of waiting for an interrupt and having that interrupt queue fill up. You've got a single core that's just pulling on a single network interface again and again and just grabbing that data. And for web browsing on a normal PC, that's a terrible use of a core. But on a high performance machine where we know that there is always going to be data ready and we need to get that data off that device as fast as possible before the buffer overflows, that is an ideal way to thread your application, is to assign the I/O threading or the I/O polling to a single core. So immediately our direct connect topology has reduced our costs and increased performance. And it further increases performance when you start to look at that memory bandwidth diagram again. Because right off the bat, you'll see that we're moving our data directly into our application instead of into a kernel buffer. And that's because DPDK enables kernel bypass. The DPDK method of moving data through your network stack allows you to pull that device driver into the user space, actually embedded in your application, so that you're pulling data directly into a buffer that your application can access. And so we pull that data into our application, we read it back out, do a little bit of processing, put it back in, and then we go to write it to disk. Again, you have to go back through those same write it to a kernel buffer, then let that kernel buffer move it to the storage device. But there are also libraries out there that will allow you to do kernel bypass on the data storage side of things as well. The Linux kernel is starting to introduce libraries that do this that maybe future versions of Ubuntu will have installed by default. Intel, in addition to developing DPDK, also develops SPDK, the Storage Performance Development Kit, and that allows kernel bypass technology that would write to the disk in the same way that it pulls data off a network card, with that pulling architecture that allows you to reduce memory copies and increase performance in those high throughput cases. So when you're looking at system topology, you need to think about, how am I connecting all of these devices to my machine? How am I actually pulling that data into the system memory? And then how many copies of that, or what kind of impact does that have on my memory bandwidth? And so these are some of there's a lot of considerations you have to make at the system level, but these are some of the biggest ones that if you don't analyze before you purchase a system, you're very quickly going to reach limitations early on in development. And so here's what it might look like if we actually start to connect everything up. What does the data movement through a system look like? So here, for example, we have 16 N320s, and each one of those is sending 1 gigabyte of data over the 10 gigabit connection. We connect 4 of them to a network card in slot 0. We connect 4 of them to a network card in slot 1. And then additionally, we connect 4 more to the network card connected to slot 0 and CPU 1, and slot 1 connected to CPU 1. And what this allows us to do is it allows us to balance, to distribute the data movement across our CPUs, because when we're pulling this data in, again, we're assigning cores from each one of these CPUs to do nothing but pull data from these devices. So we don't want to have all of these devices assigned to a single CPU, because then every core on that CPU is doing nothing but pulling data in. We want to evenly distribute the load, and we want to balance it. We want to balance it across the CPUs, and then we want to distribute it through the CPU by using those core affinity techniques that things like DPDK enable. And then once we've got all that data pulled up into system memory, we want to push it back down. And when you balance it like this, it gives you good access to additional processors like those GPU. I left the data movement arrows off for the GPU and the memory, but what you'll see is with something like this, with the numbers that we're talking about on this specific slide, you could very easily add a down to GPU 0 and back up to the CPU, and then back down to GPU 1 and back up to the CPU, and then finally back down to those NVMe drives, which are our storage units. So this, you have to sort of plan out where is the data moving through at each link in the chain, and does your system provide the resources necessary to actually move that data from a processing standpoint, from a memory bandwidth standpoint, from a PCIe throughput standpoint. And so system topology directly impacts what sort of streaming numbers you're going to be able to hit. A little bit of planning up front will save you a lot of heartache down the line when you realize you're not going to get even a quarter of the performance you were hoping to. But if you plan it out and you research your systems accordingly, you can hit those throughput numbers. But in order to hit those throughput numbers, even if you have planned all this out, is purchasing hardware that can actually hit the throughput rates at each link in the chain that we've been talking about. Making sure that it has enough PCIe slots, making sure that it's got enough memory bandwidth, making sure that you've got enough cores. So let's take a look at what are some examples of hardware that you go out and purchase right now that will enable a system topology that we just looked at. And so one of the first servers that you would want to look at, one of the types of servers that you would want to look at is what's called a GPU server. So first off, the two things there. One is it's a server, not a desktop. If the throughput rates we're talking about, it's going to be very difficult to find any desktop that has the PCIe slot count that we would need in order to move the data into a system like this, process it using our heterogeneous processing like FPGAs, GPUs, CPUs, and then store it to disk. You're going to need a rack-mounted server in order to handle the throughputs and the processing that we're talking about in an SDR application like this. And then, now that we know that we need a server, what kind of server. There are a lot of different types of servers out there that serve different applications. We're not talking about a large database server. What we want is something called a GPU server, which is designed specifically for processing data. GPU servers are very popular right now. They're one of the newest entries to most server vendors' lineup. And the reason they're attractive to an application like ours is, first off, it's got a lot of externally accessible PCIe slots. Sometimes those PCIe slots are buried deep within the server and they're not externally available. But a lot of what you'll find with GPU servers is they are externally accessible. So you can see in this image here, we've got 8 GPUs and all of them go directly to the back of the CPU. So you could replace those GPUs with networking cards and you can attach the networking cables directly to those cards if you want to. And second, they've got a lot of open PCIe slots. Some servers that, for example, a storage server who's designed primarily to store data, but that data doesn't necessarily come in or go out at high throughput rates, will instead redirect those PCIe lanes to a whole bunch of storage drives. That's not what we want. We want just open PCIe slots so that we can decide what we want to do with it. Maybe use some network cards, some GPUs, some NVMe drives. Those open slots are what we want, and the GPU servers provide them. And also, third, balanced I/O. This isn't obvious at first when you're looking at these servers, but what you'll see a lot of times is maybe they do have 5, 6, 7 open PCIe slots, but what you'll see is like 5 of those 7 PCIe slots go to a single CPU, and only 2 of those open PCIe slots go to the other CPU. And this creates an imbalanced access pattern that forces your application to become NUMA aware. NUMA being a non-uniform memory access, where you have to start, where now you're suddenly aware that, oh, even though all these channels came in through CPU 0, I want the data to now be transferred to the memory banks connected to CPU 1. Once you start engaging in these NUMA crossings with your data, things fall off a cliff very quickly if you're not very careful with how you move data between those zones. So, but with balanced I/O, you don't have to worry about that. The data goes from the network card to the CPU, and then back down to the GPU, and back up to the CPU, and then back down to the storage without ever doing any of those NUMA crossings, unless you want to, say you're aggregating the data. And then finally, we've touched on this a couple times. You get flexible slot usage. Put a GPU in those slots because they're double wide and they've got access to power connectors. Put some storage in there. These are directly connected to the CPU, no PCIe switches, so you don't have to worry about any NVMe compatibility issues. Or put network cards in there. Network cards can only go in slots that are externally accessible. So very flexible servers that sort of check all the boxes that we would need for an SDR application. And you can find these from most server vendors these days. This is a very popular model. It's the newest lineup to most of their server selection, but they're all selling them these days. So now that we know that we want a GPU server, there are 2 lines that you would look at from there. Do I want an AMD GPU server or do I want an Intel GPU server? And for our application, we're probably going to be using an AMD GPU server, at least in the 2-socket servers that we would be looking at. And let me explain why. So the AMD servers, they have higher core counts than the Intel versions. They have higher memory throughput. They have higher memory capacity. They have more PCIe lanes, a lot more PCIe lanes. And those PCIe lanes are Gen 4 as opposed to Gen 3. So all of the key performance metrics pretty much across the board end up in AMD's column. The one reason you wouldn't have used AMD in previous generations is that in previous generations they had non-uniform resource access. And so that's what's shown in the slide here, is the first generation of Epye server chips. They had 4 chiplets, is what they called them, and each one of those chiplets had its own PCIe lanes and its own memory controller. And if one of the other chiplets needed to access a resource connected to another chiplet, it would need to do a NUMA crossing. And as we talked about earlier, NUMA crossings very quickly start to sap your system of its performance, because it effectively cuts your memory bandwidth in half, because you now, instead of just servicing using the memory for your own for its own cores. Now it has to provide memory access for cores on other chips. It's not the kind of access pattern that anyone would want, and it pretty much was a non-starter for any of the applications we looked into. However, in the most recent lineup, they've solved this. They added a big I/O die right in the middle of the CPU, and that I/O die is connected to all the PCIe lanes, and it's connected to all the memory controllers. And the chiplets that contain the cores talk to the I/O die, and that gives them all uniform resource access. That's what we want, the uniform resource access. With that first generation, each CPU was effectively 4 NUMA zones. With the second gen, it's just 1 NUMA zone. 1 NUMA zone is basically just a normal processor. With Intel Xeon, you get this monolithic die as opposed to these separate chiplets, and that enables a very uniform resource access. They've always had these. And it's actually still a little bit more uniform than AMD is, even with that second generation, if you're doing core-to-core data movement. That's not that common, and the advantage in core-to-core isn't that great. So generally speaking, the only advantage that Xeons have in the current generation is if you need a 4 or 8 socket server. That's the primary reason you would use a Xeon chip if you're building out a system these days for SDR, and you're curious what the advantage of each one is. So let's go ahead and take a look at what one would look like. So in the dual socket case, this would be the kind of server you would want to look at if you were looking to ingest and then process and then store something like 16 gigabytes of data per second, maybe even up to 32 gigabytes per second might be the very, very highest you could get to. And this is the 4124GS from Supermicro is an example of one such server that enables something like this. It would have 10 PCIe slots with that balanced I/O that we talked about that are all externally accessible. And this is efficient across many channel counts. If you've got, say, 8 SDRs and you want to pull 8 gigabytes per second, you can still use a server like this cost efficiently. Or if you want to scale it up to 16 devices running at 32 channels, doing 32 gigabytes a second, you could still use a system like this. So a lot of flexibility with that dual socket. This is sort of the sweet spot that hits a wide range of those channel counts and allows you to cost efficiently scale up, especially because it's got Gen 4 PCIe lanes. Those will scale well into the future. But if we want to take our channel count to the very top of what's possible right now, we would want to use a quad socket server. And Xeon is the only option there. You have to use Xeon if you want quad socket or 8 socket. And this is an example of one such server, the 8049U from Supermicro. And it has 16 PCIe slots. And it's got 4 CPUs, so you will be able to keep up with the data rates even at and beyond 32 gigabytes, maybe even up to as high as 64 gigabytes per second. It would be challenging to hit those rates, but it is possible with something like this. The downside to this type of server, first off, it's a lot more expensive. It's twice as expensive as that other server we were looking at, that dual socket AMD. It's probably more than twice as expensive actually. And also the I/O is unbalanced. This is not a GPU server. This is just a high-end general purpose server that will serve all sorts of different needs. And unfortunately, the I/O on this is not balanced. Some CPUs will have 6 PCIe lanes, some will have 8 PCIe lanes, others will have 2 PCIe lanes. You're just not going to get, most of the servers that are not GPU servers do not have balanced I/O. And so you're likely to have to deal with some amount of NUMA crossings. You generally want NUMA crossings to be as low as possible. It's okay if it's not 0, but as the amount of data that's crossing between zones starts to increase, the more likely you are to not be able to hit your performance numbers. But that's something to keep aware of with these higher channel count systems that require something like this. Additionally, not all the slots are full height, full length. With that GPU server, you saw you could get like a double wide GPU that was full height, that was the full length in there, and you can get 8 of them in there. You're not going to get that in a server like this. There's just not enough room for 16 full height, full length, double wide GPUs. So some of them are going to be low profile slots that just aren't going to be able to fit anything except, say, a network card, for example. So you kind of have to do a little bit of rearranging there, a bit of a puzzle to get all the network cards you want connected to each one of the CPUs, and then a little bit of storage connected to each one of the CPUs, and then maybe one of the CPUs has a couple of the GPUs, or the GPUs connected to it, and that's where all the NUMA crossings come from. So that's a summary of what it looks like to gather requirements for an SDR system. In this case, we've been looking at some of the cognitive systems in the EW and the RF space. And then once we have those requirements, what sort of topology do we want to create for them? If those are network devices, how do we pull that data into our system? And then once we've identified an ideal system topology, what's actually out there? What can we go and buy? So this is just a recap of those 3 points. Hope you enjoyed listening. I appreciate your time. Thank you.